This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Alright, before we close up shop, let's take a quick look at current flow and balanced delta configurations, minus the lengthy preamble. We should experience a similar phenomenon, notably cyclically pulsating current at all times in accordance with Kirchhoff's current law. Recall during the three-phase AC examples lecture, available at the Big Bad Tech channel, we analyzed a balanced delta consisting of three impedance elements, ZAB, ZBC, and ZCA, each having an impedance of 425 ohms at an angle of 40 degrees in a 120 volt line to neutral, 208 volt line to line three-phase AC system. In the course of our analysis, we learned impedance element ZAB drew 489.4 milliamperes at an angle of negative 40 degrees. Impedance element Z2 drew 489.4 milliamperes at an angle of negative 160 degrees. And impedance element Z3 drew 489.4 milliamperes at an angle of 80 degrees. IAB is defined as traveling from A to B. IBC travels B to C, and ICA travels C to A. You will note current through each balanced impedance is equal in magnitude and phase shifted from each other by a relative 120 degrees, as we'd expect for a balanced delta configuration. Additionally, we learned current in the lines for this balanced delta configuration is equal to square root 3 times load current and phase shifted from the nearest load current by a relative 30 degrees. I1 equals 847.7 milliamperes at an angle of negative 70 degrees. I2 is 847.7 milliamperes at an angle of 170 degrees. And I3 equals 847.7 milliamperes at an angle of 50 degrees. I1 is defined as traveling into A. I2 travels into B. And I3 travels into C. You'll again note line current for this balanced delta is equal in magnitude and phase shifted from each other by a relative 120 degrees, as we'd expect. What in the hell does this mean? This most assuredly does not mean 489.4 milliamperes chases its tail around the delta, nor does it mean 847.7 milliamperes simultaneously pours into the delta from three different corners. These are phasor values and are merely shorthand representations of time-variant sinusoidal phenomenon. As previously, I invite you to determine the peak values for both load and line current for this balanced delta configuration. By all means, pause the lecture and do so now. If you're tracking, you should have obtained the following values. Load current will have a peak value of 692.1 milliamperes, and line current will have a peak value of 1,198.4 milliamperes, almost 1.2 amps. Let's again assume a 50 Hz frequency for the purposes of easily divisible instantaneous analysis. This means IAB as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time minus a phase shift of 40 degrees. Similarly, IBC as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time minus a phase shift of 160 degrees. And ICA as a function of time can be written as 692.1 milliamperes times the sine of 360 times 50 times time plus a phase shift of 80 degrees. Similarly, I1 as a function of time can be written as 1,198.4 milliamperes times the sine of 360 times 50 times time minus a phase shift of 70 degrees. I2 as a function of time can be written as 1,198.4 milliamperes times the sine of 360 times 50 times time plus a phase shift of 170 degrees. And finally, I3 as a function of time can be written as the 1,198.4 milliamperes times the sine of 360 times 50 times time plus a phase shift of 50 degrees. Let us not dilly-dally with tedious manual analysis. Take it away, computer. Here's instantaneous current values for one full 20 millisecond cycle in 1 millisecond increments. To expedite this lecture, we'll examine this data in 2 millisecond increments. Let's take a close look at a couple entries. At t equals 0 milliseconds, negative 444.9 milliamperes travels through impedance element ZAB from A to B, where the negative sign really means positive 444.9 milliamperes of current actually travels B to A. Negative 236.7 milliamperes of current travels through impedance element ZBC from B to C, where again the negative sign really means positive 236.7 milliamperes of current actually travels C to B. and 681.6 milliamperes of current travels through impedance element ZCA from C to A. Similarly, at t equals 0 milliseconds, negative 1,126.5 milliamperes of current enters node A, where the negative sign really means positive 1,126.5 milliamperes of current actually leaves node A. Positive 208.2 milliamperes of current enters node B, and 918.4 milliamperes of current enters node C. Consider an application of Kirchhoff's current law at node A. 444.9 milliamperes of current enters node A through impedance element ZAB. 681.6 milliamperes of current enters node A through impedance element ZCA. And finally, 1,126.5 milliamperes of current leaves node A through line 1. 444.9 plus 681.6 does in fact equal 1,126.5. Similarly, consider another application of Kirchhoff's current law at node B. 236.7 milliamperes of current enters node B through impedance element ZBC. 208.2 milliamperes of current enters node B through line 2. And finally, 444.9 milliamperes of current leaves node B through impedance element ZAB. 236.7 plus 208.2 does in fact equal 444.9. Finally, consider an application of Kirchhoff's current law at node C. 918.4 milliamperes of current enters node C through line 3. 681.6 milliamperes of current leaves node C through impedance element ZCA. Finally, 236.7 milliamperes of current leaves node C through impedance element ZBC. 918.4 does in fact equal 681.6 plus 236.7. In all cases, what came in does indeed come out. Even when we don't concern ourselves with the internal workings of the balanced delta, but rather restrict our analysis to just the lines, Kirchhoff's current law holds true. If this is an unknown box with 3 lines leading to it, we could still apply Kirchhoff's current law. At t equals 0 milliseconds, line 2 dumps 208.2 milliamperes of current into the balanced delta at node B, and line 3 dumps 918.4 milliamperes of current into the balanced delta at node C. As a result, line 1 exhausts 208.2 plus 918.4, or 1,126.5 milliamperes from the balanced delta at node A. Let's dispense with Kirchhoff's current law analysis and examine subsequent 2 millisecond steps rather quickly. If you want to do it in 1 millisecond and check these results using Kirchhoff's current law, be my guest and do so at any time. At t equals 2 milliseconds, 48.3 milliamperes of current travels B to A. 573.8 milliamperes of current travels C to B. And 622.1 milliamperes of current travels C to A. 670.4 milliamperes leaves node A. 525.5 milliamperes of current leaves node B, and 1,195.9 milliamperes of current enters node C. At t equals 4 milliseconds, 366.8 milliamperes of current travels A to B. 691.7 milliamperes of current travels C to B, and 324.9 milliamperes of current travels C to A. 41.8 milliamperes of current enters node A. 1,058.5 milliamperes of current leaves node B, and 1,016.7 milliamperes of current enters node C. At t equals 6 milliseconds, 641.7 milliamperes of current travels A to B. 545.4 milliamperes of current travels C to B, and 96.3 milliamperes of current travels A to C. 738.1 milliamperes of current enters node A. 1,187.2 milliamperes of current leaves node B, and 449.1 milliamperes of current enters node C. At time t equals 8 milliseconds, 671.6 milliamperes of current travels A to B, 190.8 milliamperes of current travels C to B, and 480.8 milliamperes of current travels A to C. 1,152.4 milliamperes of current enters node A, 862.4 milliamperes of current leaves node B, and an additional 290 milliamperes of current leaves node C. All right, halfway there. At t equals 10 milliseconds, 444.9 milliamperes of current travels A to B, 236.7 milliamperes of current travels B to C, and 681.6 milliamperes of current travels A to C. 1,126.5 milliamperes of current enters node A, 208.2 milliamperes of current leaves node B, and an additional 918.4 milliamperes of current leaves node C. At t equals 12 milliseconds, 48.3 milliamperes of current travels A to B. 573.8 milliamperes of current travels B to C, and 622.1 milliamperes of current travels A to C. 670 milliamperes of current enters node A, 525.5 milliamperes of current enters node B, and 1,195.9 milliamperes leaves node C. At t equals 14 milliseconds, 366.8 milliamperes of current travels B to A, 691.7 milliamperes of current travels B to C, and 324.9 milliamperes of current travels A to C. 41.8 milliamperes of current leaves node A, 1,058.5 milliamperes of current enters node B, and 1,016.7 milliamperes of current leaves node C. At t equals 16 milliseconds, 641.7 milliamperes of current travels B to A, 545.4 milliamperes of current travels B to C, and 96.3 milliamperes of current travels C to A. 738.1 milliamperes of current leaves node A, 1,187.2 milliamperes of current enters node B, and 449.1 milliamperes of current leaves node C. At t equals 18 milliseconds, 671.6 milliamperes of current travels B to A, 190.8 milliamperes of current travels B to C, and 480.8 milliamperes of current travels C to A. 1,152.4 milliamperes of current leaves node A, 862.4 milliamperes of current enters node B, and 290 milliamperes of current leaves node C. Finally, at t equals 20 milliseconds, the process again repeats itself. As previously, take a moment to think about what happened for the full cycle. Again, did you see what I did? If not, I'm encouraging you to rewind the lecture to the beginning of the step-by-step analysis, turn off the sound, and turn up the speed. What you should see is current pulsating around and around the balanced delta. Sometimes a large burst comes in one node, splits, and travels through two legs. Sometimes the outflow of two smaller legs join up, such that a larger burst comes out one line. Current through various legs and various lines rises, peaks, and falls positively, and similarly rises, peaks, and falls negatively. Importantly, at all times, Kirchhoff's current law holds true, and what comes in does indeed come out. As further proof, overlay the plots of line current as a function of time with one another. During this time span, current comes into the delta through line 1. During these time spans, current comes into the delta through line 2. During these time spans, current comes into the delta through line 3. Similarly, during these time spans, current leaves the delta via line 1. During this time span, current leaves the delta through line 2. And finally, during this time span, current leaves the delta via line 3. What you get is a cyclical flow around each corner of the delta such that each load in the delta experiences the same rise and fall but is sequentially offset from one another, working in a coordinated fashion. Again, can you or can you not dig this on the same level that I do? All other valid reasons aside, it's perhaps because of three-phase AC's innate ability to create a rotating magnetic field that three-phase AC is the primary power of choice for industrial systems and large generation facilities. Alright, hopefully this tedious walkthrough has clarified what exactly occurs inside balanced Y and delta configurations. Keep in mind this iterative analysis technique is not limited to balanced configurations, but can also be extended into unbalanced configurations as well if you've got the interest and motivation. All it takes is intermediate spreadsheet skills, or lacking a computer and spreadsheet software, a calculator, pencil, paper, and a couple hours to kill. Hopefully this lecture saved you some time. You've got a better appreciation for what phasor quantities truly represent in three-phase AC systems. In conclusion, this lecture examines step-by-step instantaneous current flow inside balanced Y and delta configured loads in three-phase AC systems. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.